Hello and welcome to this talk titled Go Channels Demystified. The agenda for today is what are Go channels? Why should we use Go channels? How do we use Go channels for different things? And when and where to use Go channels to get the best use out of them. My name is Mofi. I'm a senior developer advocate at Vonage. I mostly work on client SDK stuff. I collect stickers and I also write Go and JavaScript code. You can find me on the internet at Moficodes on Twitter, YouTube, dev.to, Medium, what have you. So let's get started. If you want to get access to the slides in this talk, you can go to tiny.cc/go-channel. That will be the link to this slide that we're looking at right now. And there are some code examples in this slides. There are also, you're gonna see some icons of cross and check mark. They don't mean the code is correct or incorrect. They just mean if you were to copy this code into your IDE and try to run it, the one with the check mark would be able to compile and run, and one with the X next to it won't be able to compile and run. So let's talk about what channels are. If you have been around and writing some Go code in the past, you probably have come across channels, and you have probably used channels as well if you wrote any concurrent application in Go. So channels are a typed conduit through which you can send and receive values with the channel operator. So typed conduit is just a synonym for channels, and it is a way to send and receive information. And when you're writing Go code and using channels, you have probably seen this arrow operator with the less than sign and the dash. Some of the other features and characteristics of channels is that channels are Go routine safe. You can pass data between Go routines with channels. Channels can block and unblock. Can block and unblock channels. So one channel can block or unblock other channels by blocking and unblocking other Go routines. And it works like a queue, even for an unbuffered channel. And for a buffered channel, definitely works like a queue. The thing that was done first gets executed first. Channels are typed, so each of the channel that you create has certain type, and you can only send data of that type. And channels can be sending, receiving, or both. So you can create a channel that are sending only, are receiving only, or channels, just a general channels that you can both send and receive. So let's talk about unbuffered channels. So unbuffered channels are blocking. Each send must have a receive. So unbuffered channel is where you don't really have any extra capacity. Every time you want to send something, someone on the other side has to receive it for you to be able to send it. For example, this is an example of an unbuffered channel. The cross on the corner denotes that this code will actually deadlock and won't actually compile. So if you write this code out in your IDE, you won't be able to see the output. So what we're doing here is creating a channel with the make keyword. We're creating an int typed channel on this line here. Then we're trying to send 1 to that channel, and the line after that we're trying to get the value out of that channel and put it into D and trying to print that value out. But because it's an unbuffered channel in the same Go routine, this operation here, C passing 1 to C, will deadlock. But again, we'll explain why that happens in a minute. This, on the other hand, we have a send function. We create, we pass the channel to it, and we send 1 in this function here. And this line, we just create a new Go routine and call the send with the channel that we created before. And then we try to receive the data on line here, line about 7 or 8 here. We try to get the value out of C, and we print the data out. So if we were to write this function and print it out, we would see that it prints out 1. So what is happening is there is a separate Go routine where we send the value and immediately read that value from this Go routine, and we can print that value out. So these are examples of unbuffered channels. We can also see send only and receive only channels. We probably already seen that example in the previous if you were paying attention, but we're going to see an example again. We can either create a send or receive only channel, or we can create a regular channel but be passing that to a function that is expecting it to be send and receive. So the example of that would be something like this. In this case, we're creating a receive-only channel here where we only expect to receive from this channel. If I try to send something to this channel, that would be a problem. And in this case, we're creating a send-only channel. We can only send data to it. We can't receive data from it. And again, the X denote this would compile, mainly because we're creating variables that are not using here. So that's why this code will complain and compile, not compile. Also, we can create just a general function, a general channel that is both receive and send only. But in the function receive, here we can expect receive only channel. So when we pass this channel into receive here, inside the scope of the receive, this channel is receive only. Although the channel itself is send only, we can convert that into receive only. Although the channel is possible, like it's available for both receive and send, inside this function, this is receive only, and inside this send function, this is send only. This is very useful when you're trying to write code to kind of lock you into either it's receive or send so that you don't write a wrong code by mistake. Your IDE and your compiler will help you make sure the place you want to receive only gives you the permission to receive and vice versa. So buffered channels are just like unbuffered channels, except there is a size up to which it is buffered. So what that means is if you have a buffered channel of size 3, you can send 3 things into the channel before you have to have a receive, because it has a capacity of 3 things. It can hold on to 3 things before someone needs to take that receive on the other end. So example of a buffered channel here is we have a channel C. The syntax is almost identical, but instead we have a number after the type. So channel int and 1. So I can, this code, where in the first example, this code didn't went to deadlock because there was no receiver available. Here I can send 1 and I'll fill up the buffer. And after that, I can just receive that 1 from this channel onto D and print that out. And this code will compile and print 1. So channel, based on channel state on any channel, these are the different things that can happen. So if the channel is nil, so you could just created a channel variable without giving it a type or calling make. So if you have a nil channel, if you try to receive from it, it will block. If you try to send something on it, it will also block. So nil channel always blocks. If you have a channel that is open and available to take information, when you try to receive, you will get the value. When you try to send, it will write the value. And if it's a closed channel, when you try to receive something, you'll always get the default value and the second value of false. And if you try to send something to a closed channel, that's a panic. If I were to extend that list a little bit more to showcase all the different states that you can have, we can actually see this. So the yellows and the oranges and the reds are the ones to look out for that can, you have to be careful not to be in a position where your code is panicking or you're getting some compilation errors. Compilation errors are quite nice because these are errors that you can see before your code actually is compiled. So you can fix them. The main compilation error would be if you're trying to receive from if you're trying to send to a receive only channel. So that's where like using functions to convert our send and receive channel into a send or receive channel, depending on what we need to use. So if you were to try, like if let's say you have a function that is expecting a receive only channel and inside the function you're trying to send something, that will be a compilation error. Your Go IDE like VS Code or Golang will then give you some red squigglies to tell you that this is not a permitted operation. And the same is for send only channel trying to receive data from it. It will be a compilation error. If your code also is like if you try to close a receive only channel, that's also a compilation error because a receive only channel is not supposed to be closed by the person, like by the function that has access to the receive only channel. That's where you want to make sure that the person, either the creator of the channel, which has access to the full channel, or the sender is closing the channel, not the receiver. A couple of the panic states are when you're trying to send to a closed channel, that's a panic. If you're trying to close a closed channel, that's also a panic. If you're trying to close a nil channel, that will also cause a panic. And there are some other block condition is that if it's a channel is open and empty and you try to receive something from it, that will block. If a channel is open and full, you're trying to send to it, it's going to block as well. So you can imagine unbuffered channel as both open and empty for receive and open and full for send. That's why it blocks if there is no other receiver on the other end. So again, the thing we saw before, nil channels always block. So if you have a nil channel, it will always block. There are some useful patterns by turning a channel nil so that you can block certain things. But yeah, if you have a nil channel, that will always block. So for example, if you have this line of code, if you create a var_c of channel int, this channel doesn't have any data, it's a nil channel. If you try to send something to it or receive something from it, they will both block. In this example, the code will deadlock. It'll never even go to line where d equals channel c is here. So it will just block here and it'll deadlock eventually. And closed channel never blocks. So if you have a closed channel, you're trying to receive from it, you'll always get some data. You'll get the default value for the type. For example, if you have an int channel and you close it and you try to receive from it, you'll always get 0 from it. So to understand what is going on, so let's say you have a channel C, typed int, you close it, then you try to receive some data and print it, you will actually get output here. You will get it printed 0. So what if you actually have a regular channel where you are sending 0? So this, right, if you're sending 0 and you print 0, you don't really know whether or not it's open or closed. To get rid of that confusion, because closed channel always return the default value for type, it also actually returns a second value that denotes if the channel is open or not. So in our example, if we were to, let's say we have a channel of a buffered channel of size 1, we're sending 1 to it, and we're trying to read that value and OK, we will see that the prints 1 and true because the value is 1 and the OK is true. OK basically means channel is still open. Now, if we close the channel and we try to read data from the channel again, that would also work. We'll get the value 0, but the OK in this case will give us false because the channel is no longer open. One of the very famous quote from Rob Pike on Gopherfest 2015 was, "Channels orchestrate, mutexes serialize." And if you're familiar with concurrency in other languages or even Go does have access to mutexes that you can use to kind of write concurrent application. But in this talk, we're talking about channels. And channels, the way they work together, it helps you orchestrate your application, whereas mutexes lets you control memory access and serialize your concurrent application and synchronize them, that using mutexes and controlling what memory you have access to. So let's talk a little bit about select. So select lets you select one of the channels that you're looking for right now. So the select statement lets go routine wait on multiple communication operations. So you have multiple channels, they can be inside a select block, and if any of them returns data or any of the states are true, you will execute that command. So select blocks until one of its cases can run, then it executes that case. Select in syntax looks a lot more like switch cases, but it is basically listening over multiple channels instead of just multiple condition that executes, only one condition executes. It is possible that multiple of the select channels that are waiting on became available at the same time. In that case, select will randomly select one if multiple became available at the same time. So select is blocking. All select command that you run is blocking. If none of the condition in select are true or can never be true, select can eventually deadlock. So in this case, if you just run select like this command doesn't have any condition whatsoever, but this will block forever and you will get to deadlock. So yeah, as I said, it's like switch case, but not really, because switch case, usually what you have is multiple condition and only one can be true in terms, or the first one to be true gets executed. In terms of select, multiple can be true at the same time and only one gets randomly selected. So when you are selecting on multiple things, when you're running a switch case, usually what you do is you run the switch case on the same variable on multiple types of values of that same variable. When you're writing select, however, you can select on any and all channels that you have in the scope, right? You don't really care about are these channels related to each other in any way. You just want to select over them no matter what. So the way you select and how you compose your application, it's left to the user. Go doesn't really dictate how you can or cannot use select. That's a freedom, but also a responsibility for us as users. Also, let's talk about ForSelect next. So ForSelect is like select, but in a for loop. So if you want to continuously look at bunch of different channels and wait for them to be true, you can run them in ForSelect and wait for them to become true. So it's a for loop, and there's a select inside it. And if you're trying to do a long running select operation, that's when you use ForSelect. For loop can be up to some limit or indefinite. Usually you are doing that for an operation that you know will happen many times over, but you don't know exactly how many times. You can just write a ForSelect and it will continue to happen. For example, in this case, we're creating a channel, and we have that channel. We have two select commands. One is some data coming out of CH and putting it to D, and we're printing data. And the other one is just a built-in time channel where after 3 seconds, the time sub get printed. So in this example, we will just be printing time sub every 3 seconds forever, because we're doing nothing that closes out of the channel, we're data out of the channel CH, because we're not sending anything to channel CH. So these are all the fundamental things you need to know to be able to use channels. So at this point, you know all that channel can do, how channel syntaxes work. And honestly speaking, there is not much more to it in terms of syntax in channels. But now we'll be talking about two more sides of things. One would be how channels actually work underneath, and one is where and how you use channels to build different concurrent patterns. So why would we want to use channels, right? So do not communicate by sharing memory. Instead, share memory by communicating. That's one other famous Go proverb by Rob Pike. And to understand where this actually becomes useful in Go is the idea of channels and how you use channels to communicate with other Go routines, right? When you have mutexes, what you do is you have a shared memory and use the mutex to lock and unlock that shared memory, so multiple Go routines can synchronize among with this shared memory. But when you have channels, what you can do instead is have all the Go routines in all over the place running, but pass information between them using channels. And that's where the share memory by communicating comes along. Instead of having a shared memory location, now you're just passing information from one Go routine to another via channels. So if you, in the 1980s, there was a computing principle called CSP, and it is called Communicating Sequential Process. So it's a paper by Anthony Hoare in 1978. It's a way for creating concurrent application via message passing. Other language that is also very famous and uses this particular system is Erlang, and Go uses channels to pass messages to build concurrent application. So again, that's kind of like the background where the idea of channels comes along. Now let's talk about some of the other theoretical things that we should understand before we can appreciate channels and Go routines a little bit better. So in our operating system, there is a scheduler that schedules things. And one of the key things we have are processes. We have a lot of processes running in our machines any given time. And each of our processes is basically a program in execution, right? In this case, I'm using Google Chrome as my browser. That's a process that's running. I am using my camera. That's a process that's running. I'm using a bunch of other applications that's running. Each of them are at least one, in many cases, many processes running in my computer right now. And execution of a process progresses in a sequential manner. A process starts, it does something, at some point it gets killed or finishes, and it just stops running the process. So if you want to see more like a diagram of flow, how the process does something, a new process is created, it gets admitted to the operating system, at some point it becomes ready, and whenever the operating system has the capacity to run it, the scheduler then sends it to running. And you could do some sort of like interrupt to get it back to ready, or let's say you are waiting on some IO event or some sort of wait or sleep, it can go to waiting ready and running, and at some point it will exit and will get to kill state. So that's how pretty much every single application in your computer would be running. There could be some sub-states, but these are the main big ones. After processes, a little bit smaller thing that is in our machine are threads. So threads are a path of execution within a process. A single process can and almost certainly will have multiple threads. So a thread has also similar states like a process does. It is born, it becomes ready. At some point, it gets to running. For certain things, it can get to blocked. Blocked as in like it's blocked on or blocked on something. Some other process stopped, or the same process blocks the particular thread. It can be also waiting for I/O or printer or whatever it can be waiting on, or it could be sleeping. You can send a thread to sleep. After all of that, after the block is unblocked, the waiting is done, or the sleeping is ending, the thread goes back to ready, and it can go back to running again once it becomes available, like the process has more threads available. And at some point, when the thread has done all the work it needs to do, it can go to a dead state where the thread is killed. So this is my machine. I took a screenshot of my activity monitor, and on the left, this big list are all the different processes that are running, that were running on my machine at that time. And you can see there's multiple different processes. I have things like VS Code. You can think I have Slack, Google Chrome that I'm recording like showing my slides off right now. I have VS Code, and a bunch of other things. And on the right side, you can also see there's another column called threads, and you can see each of my process are using anywhere from 2 all the way up to 78 different threads. And depending on what kind of process I'm running, they could be asking for even more threads. So as you can see, a single process is here using a lot of different threads. So finally, let's talk about Go routines. So a lot of people, when they talk about Go and why it's great for concurrent application, will talk about Go routines. And Go routines are functions or methods that run concurrently with other functions or methods. Go routines can be thought of as lightweight thread. It's user space threads that are managed by the Go runtime and not by the operating system. So the cost of creating a Go routine is extremely small compared to thread. Whereas a thread can take up to milliseconds to create, a Go routine is in the nanosecond scale to create new Go routines. Go routine also have multiple states. So you have create. Then after it's created, it goes to a queue. Once the queue is ready, it can go to executing on a thread. And then from there, it can either be interrupted by sleep or syscall, or get blocked by something, and eventually it goes back to the queue, goes to executing, and at some point it exits. So the reason we're talking about Go routines and in the scope of channels, because when you are dealing with channels, when you're doing something on channels, this block can come into play, and this sleep and syscall can come into play to control the communication of channels between multiple Go routines. So let's talk a little bit about Go scheduler to just appreciate all the things that Go runtime does for us when you're trying to write concurrent application. Go is a M-to-N scheduling. What that basically means is you have M operating system threads and you have N Go routines. And any given time, those M threads will be used to schedule the N Go routines. So M thread schedules N Go routines. That's what it means by M-to-N scheduling. So let's take a look at what would look like a usual execution of a Go application. So you have this P is the scheduling context. So depending on how many operating CPU cores you have a number of set Ps. You could increase the number of Ps, but by default, having the number of Ps equal to number of CPU cores gives you the best performance usually. So that's where you probably should stick to. So you have a number of P. In this imaginary example, we have a 2-core CPU, so you have 2 of these Ps. We also have a global run queue where we have a bunch of Gs. Gs are the Go routines that we're trying to execute. For each of the P, we have also a local run queue where we have a bunch of other Go routines waiting. M is an operating system thread, so we are using a single thread per scheduling context, but a single thread now we can use to schedule multiple Go routine into by using the local run queue. If the local run queue ever runs out, it can get data from global run queue. So message passing in threads. So if you have an application that is using threads and you are trying to make sure that you can pass information between threads, this is kind of what it looks like. The one colored in blue is the one currently active. So let's say you have two threads, M1 and M2, and M2 is right now waiting on some information from M1 to execute. So right now it's on waiting state. So whatever you were doing, you context switch to M1, then it becomes on executing. It's running on core C1 in your application, in your OS processor, and you pass the message off to M2. Now, after that is done, your particular M1 thread gets off the CPU core. You get it out of the core, and M2 was waiting, gets the. Did I go to? Oh no. Okay. So M2 was waiting, and then once it gets the message, it context switches. It's now in executing state, and let's say we schedule that onto core C2, and at some point after execution is done, we send a message back to M1. M1 was waiting, it becomes runnable once it gets the message, it context switches, it executes, and now we schedule that into core C3, and you go back and forth. So as you can see, every time we are passing the message, our thread has to be put into waiting and put back onto runnable and put back into executing. That is a very expensive operation. Now let's look at the same operation, but in a context of Go routine. So if you have a two Go routine, G1 and G2, which depend on the same data, which we will be sending the information back and forth. So first we context switch into G1. We start executing on thread M1 on core C1. Once we have done the execution, we send the message off to G2, which was waiting on the data. Once G2 gets the data, it goes to runnable and context switches onto running. And we can run this G2 onto the same thread on the same core, and then we send the information back to G1, which was waiting, goes to runnable, context switch executing. One of the key things to note here is that although we are context switching between G1 and G2, our thread and the CPU core we are running on doesn't need to switch, because from the operating system point of view, is the same thread doing the work. Because the Go routines are managed by our Go runtime, our CPU and our threads doesn't need to know that. Although these two pictures look very familiar and similar to each other, they are fundamentally doing two different things. In our threads example, we are constantly switching context. Our threads get scheduled and descheduled. It might even be running on different CPU cores, whereas our Go routine are running on the same CPU core on the same thread, and we're swapping all this context in the user space level. Our thread where the Go routine is running on never gets put on waiting, because our thread itself is never not doing anything. It's always be switching the context on the user space level. That's the benefit we get by using a user space thread like Go routine. So how does Go routines actually work? To be honest, channel implementation can and should be treated as a black box, because we know how channels work, we know what you can do with channels. Knowing how they work under the hood usually is not useful for most people when they're trying to write Go and trying to understand Go. So next few slides are for educational purposes only. So if you are interested in learning more about how channels work, feel free to watch the next few minutes of this talk. But again, if you don't know how they work underneath, you will be perfectly fine writing Go code and concurrent code, and really good concurrent code for that matter. So we still want to understand how this works, and for some of us, it's interesting, and it's always interesting to see how the favorite language of ours does things under the hood. So for that matter, we'll have that information. So we should be able to appreciate how channels work, and we are going to do that in the next few. And this knowledge, again, unless we're implementing a new language or trying to fix a bug, definitely ignore the next part. So with that disclaimer, let's jump in. So a channel that we use, it's underneath is just a type hchan struct, and this is the complete definition of the hchan struct. We have a bunch of fields. But the fields that we're interested in is this few. So we have this unsafe pointer, which is buff. That is the buffer, and it's a circular queue. And we also have a lock mutex here that lets us protect this buffer. So when you are creating a buffer channel, all you are creating is this circular queue that is protected by this mutex lock. That's why channels are go routine safe. We also have this lm type, which is a pointer to underscore type. This is just the unsafe version of generics. Go doesn't have generics like by default yet. Go 2 might have generics, but if for types like arrays, maps, and channels, we can have typed things, and that's underneath how they do it with reflection. We can have generics kind of, and we also have send x and receive x. This is just the count of how many elements we have in the buffer. And if it's a circular buffer, we just need to have the beginning and the end point so that you can keep track of how many things we have and where in the array we are right now. So when you call the make command to call channel, create a channel, what happens underneath is that function gets called make chan, which takes the chan type, which is in this case int. We also takes the int as like how many things you want, in this case 3, and returns you a pointer to hchan. And the pointer is important here. That's why we get a pointer to channel. That helps us because although the hchan itself gets created to the heap, it's a pointer. That's why we can just pass the channel to other functions and they point to the same heap. Although go is passed by value usually, because this is a pointer value, whatever you do to this channel happens to this channel that is in the heap. So that's why you can pass channels onto function without having to do pointer channel. So when you are sending to a channel and receiving on the other end and happening, let's say 2 go routines are running at the same time, these are the 2 things that needs to happen. And in this example, we're talking about buffered channels. The same is applicable to unbuffered channels as well. So when you're trying to send something to a channel, you will acquire the lock, the mutex, so that because you are touching the buffer, you will copy the data to the buffer, so enqueue the data, and finally release the lock. When you're trying to receive something from the channel, on the other hand, you're going to do the same thing, acquire the lock, copy from the buffer to the value, and dequeue, and then finally release the lock. So these 2 things happens. That's how we get channel send and channel receive. So this is the happy path, right? So happy path is not the only path. If this was all we needed to care about, life would have been much easier. But in a real world situation, when we write code, we have much more other condition. As we saw earlier on the chart, what are the different things that can happen? So what happens when buffer is full, or for send, or empty for receive, or channel is nil or closed, right? These are all different conditions that are possible in our channels. How do we deal with that? So remember that chart we looked at, all the different things that can happen? So let's take a look at how in the Go source code these are dealt with. So when you're trying to send something, let's say we're trying to send to, so send on a nil channel. What happens if you're trying to send to a nil channel? So we said send on a nil channel will always block, right here. Send actually anything on a nil channel other than close, receive or send, both will block. So how does that work out? So if a channel is nil, this is Go source code, by the way, and this is the number of, like, this is the link to that line of code. Although this is from few months ago, so if the source code added new things, this line number might not be right, but this code exists in the Go source code. So if a channel is nil and you have to block, what we do basically, we just send our Go routine to Go Park. So we put our Go routine to Go Park. It just goes out of context, goes to waiting until we can get to a point where you can use the Go routine and run this Go routine again. What if we try to send on closed? So if a channel is closed and you try to send it, again, we know that send on closed channel is a panic, and this is what the panic is coming from. Again, this is from the source code. So that's one of the most beautiful thing about Go, is open source. So anything that Go does, if you are not sure why that is doing something, you can always drop down to the source code level to understand it yourself. Finally, send with waiting receive. If a send has a waiting receiver, what would happen is you will just dequeue the channel, and then if that is not nil, we'll directly send it to the receiver instead of putting it onto the buffer. This is just the optimization. This is something the Go team had done to make that more efficient. But if it were to send it to the buffer and let the receiver automatically get it, that would also would have worked. But in this case, we are just sending it directly. So what just happened is there is a waiting receiver. So there is a receiver on the receive queue. We just dequeue that, and if it exists, we'll directly send the data from C to this the receive queue directly. So that's what we are trying to do here. So if you have a waiting receive queue, so you have we have a send, but there is also a waiting receive. We're just writing to the sudo G directly and call go ready on the waiting go routine to wake that up. So if there is a receive that in a go routine that's just waiting for something to be sent, we directly write to that value to the receiver and call go ready so that our go runtime can start put the other go routine onto waiting. What happens when you're trying to send something which has a full buffer? So it is full, it can no longer write anything. So what we do is create a new sudo G, add the sudo G to our send queue onto the channel. So my channel now knows I need to send more things into the queue. I set the go routine as waiting on G. So our go routine gets put on waiting, and we call go part. So our go routine gets go routine is now waiting until there is a receiver available. All of a sudden, the receiver will take the data directly from send queue, and our go routine will be put on running again whenever there's space available. And again, the same, but opposite is available for receive. So that I'll leave that to you as an exercise to look at the source code on all the different states of receive as it happens. So now let's talk about, again, we just finished up all the different, like under the hood, what are the different things that happen for Go channels to work. Now let's talk about when and where you should be using Go channels. And so when do you use Go channels? The number one place you want to use Go channel is where you need a guarantee of delivery. What I mean by that is that, let's say you have a Go function and you want to send this function here, and you are sending 5 to that channel. So if you want a guarantee of delivery, and you mean you want to wait for this number to come along, you can just wait on that channel. Because channels are synchronized, if you use an unbuffered channel, every receive will have to have a send, and every send will have to have a receive on the other end. So you can guarantee that something was received on the other end when you send something. Another thing you can do with Go channels are signal some other Go routines. For example, let's say same example here, you are like just creating a channel, you're waiting 5 seconds, you're sending some data to it, and now this main Go routine that was running is getting the data, getting unblocked, you're signaling it, it's printing the data. That is the example when you have some data with it. You can also unblock another Go routine, in this case main, without data as well. So let's say after 5 seconds, I just close the channel here, and that will just unblock this. It will get the value 0, which is useless, but it is unblocked now. Ideally, what you want to do here, instead of just getting the data, you also want to get the OK, the second variable, to check whether or not the channel was closed, or that is the regular data that came through. But you can unblock other Go routines from using channel from another Go routine. You can use channels to compose Go routine returns. So what I mean by that, you can basically use select or something to look at multiple channels at the same time, and whatever data comes back, you can return that. So that way you can compose output from multiple things into a single thing. That would be the example of something like fan-in pattern, where you have multiple Go routines doing something, and you can use a select or something to get information out of that and combine them and compose them together to return. You can also do fan out. So you can basically create multiple Go routines, and each of them will be writing to a different Go channel, and you can do work by a fan out pattern where you can create spin up multiple Go routines that is doing the work. You could also do drop. So drop is basically, in this sense, like dropping work. So if you do something like select, and with a default. So if none of the other Go channels are ready with data, you can just go to the default state and not do any work. And this is a way to implement some sort of rate limiting onto your application if you're spinning up too many resources like network, or resources like file IO, or resources like database connection, and you keeps getting more and more connection. Instead of just like bottlenecking on resources like file IO, network, or database, you can start dropping the connection and default response back something like too many connections back to the user so that they can try again back later. And this is a pattern. It's super useful when your application uses external resources. Almost all the time, you'll never get bottlenecked by Go routine itself. Go routine is very lightweight. You can spin up thousands of them without using too much resources. But the applications we built usually depend on external resource that are limited, a lot smaller compared to Go routines. Also, channels are extremely useful for pipelines. You can, if you look at how we write channels, it kind of looks like a pipeline. You take output from one, pass it to the next one, which is the definition of pipelines. So you can easily think of running some operation, getting the output of it, using that as an input to some other operation, taking the output, using that as input to the other operation, and you can compose all of that very nicely with channels. And channels can be pretty much used anywhere you want to write concurrent applications. So there are many places where you can use channels to do things. So final thoughts. Again, this talk was for teaching you how channels do the thing and how channels actually work. The concurrent patterns, there are really deep conversations can be had about what kind of concurrent patterns you should use, how they work, what are the pitfalls for one or the other. But this is not the talk for those. You can have a whole different talk about what concurrency patterns you should be using to write your application and how you can think about composing your concurrent application. But the goal of this talk was to give you an idea of how channels do the things they do, how they work, and just take a peek underneath the Go syntax and look at the Go source code on how channels are implemented. Hopefully this talk was useful. Channel is a tool for concurrency. It is not the be-all, end-all for concurrency. Channel is not the only way you can do concurrency in Go. If you're more familiar with concurrency patterns of mutexes, locks, things like ones, conditions, all the other fun stuff, you should definitely look at those for your concurrency. You should not always try to solve your problems with channels only. So like any tools, right? You shouldn't abuse it. You shouldn't think channel is the hammer and everything is a nail. We should look at our problem and see if channel is the best solution that we have available at the time. So channels are great. It's not the only way to do Go concurrency in Go. That's right. We talked about it. So if you want to learn more about channels and like some of the references I used to kind of prepare for this talk is this article from Bill Kennedy. It's a blog post. Kavya in, I think, one of the Go conferences 2017 went really deep into the Go channel itself. So if you want to understand the under the hood, how the channels work, please look at this YouTube talk on YouTube. I have the link on the slide here. And finally, Dave Cheney also has a blog post about how inner workings of channels do things. So Curious Channels is the title of that blog post. Thank you so much for listening to me for the last half an hour or so. Thank you to the organizers for giving me the opportunity to talk at this conference. I would love to hear your questions, comments, and stories. If you want to have any more questions after the talk and want to reach out and connect, please find me on Twitter at Moficodes. And with that, I thank you all and have a wonderful day.